45 minutes.
All right, thanks. Can everyone hear me? Okay. All right. So let's get started. And first, let's really look at like what this problem of black box function optimization is. So imagine we have a walking robot, and what we want to do here is to optimize its walking speed. But the only thing we can do is to test some control parameters on the robot, see how it works by executing some programs and measure its walking speed. So we can view this as a black box function where given some inputs, x, which could be the control parameters, we can observe an output, f of x, which is the walking speed. And our goal here is to iteratively test the different inputs in order to find the global optimum of this black box function, f of x. So for these type of problems, it's also appear in many, many other areas in science and engineering. So for example, tuning hyperparameters for systems like autonomous driving systems, experimental design for biology and chemistry, as well as tuning hyperparameters for machine learning algorithms like deep learning approaches. And for all these tasks, our function f is, in fact, not only a black box function, but it's also very expensive to evaluate. It can have multiple peaks, so that like traditional convex or convex optimization won't really work well. And at the same time, we don't really have gradient information in many of these cases. Not to mention that some evaluations could also be noisy. So it's really a very challenging global optimization problem for expensive functions. So if we do this task naively, perhaps we can try a grid search or random search. But that's just not very efficient because many of the evaluations could be wasted in regions that just don't have very good values. So the question is really like, how can we decide in an intelligent way like where to evaluate this function in order to recover its global optimum? Is this clear? Feel free to interrupt me at any time, okay? All right, so to do this task, one of the very popular approach is called Bayesian optimization. And the key idea here is that we're going to build a probabilistic model for our function f. And then in order to iteratively decide where to evaluate, we're going to make the decision by evaluating a function called the acquisition function. So we can optimize that acquisition function, use that argmax as the next point to evaluate that point, and add the new data into our model and repeat. So basically what we're doing here is that we're reducing the problem of optimizing a very expensive black box function into a series of optimization problems for these acquisition functions, which are cheap to evaluate, and they typically have closed form. Yeah? Yeah, very, very good question. I mean, like deciding what alpha function to use is really the key question in Bayesian optimization. In some cases, it's actually the upper bound on the function, which I'll show an example later. And in some other cases, it could be like heuristics, like information game. Uh-huh. Yeah, so yeah, that's a really good point. But in this case, because we also need to make sure that so it's very different from like convex optimization type of problem, because there could be like multiple peaks, and then there's also question of like how can we make sure we are exploring enough regions that we haven't really been there before. And if we're using if we're using a lower bound, then it's very likely that it just stays in one region that it has already seen the good value. And so that could create some problem there. So by using an upper bound, essentially what it's doing is that it's trying to be like optimistic, and that actually also encourage the algorithm to be able to like explore in a more effective way. Yeah, great question. Any other questions? Yeah. Yeah, so that's a really good question. And in fact, so in the case of Bayesian optimization, I mean, typically what I do is to look at the, because we're going to like get the evaluations of those XTs, and then basically we pick the XT that achieves the best evaluation value. And yeah, so you mean like the space that we're doing optimization in? Yeah, we're doing optimization for the acquisition function in the same space as the original function. Does that answer your question? Oh yeah, I'm gonna talk about it. Yeah, I'm gonna talk about it. I'm gonna actually show you an example soon. And so here basically there are two key questions. Where one is what type of probabilistic model we use, and then the other is the acquisition function. So I'm gonna first just talk a little bit about the kind of the probabilistic model, and then I'm gonna show you an example of the acquisition function. All right, so in the case of Bayesian optimization, I mean, typically the probabilistic model that we use is the Gaussian process. Can we get a quick show of hands? Like, how many of you know about what Gaussian processes are? Okay, cool, thanks. For those of you guys, bear with me. I'm gonna just like quickly go through some basic concepts, okay? So basically, it's a probabilistic distribution over functions, and by definition of the Gaussian process, any finite set of function values will have a multivariate Gaussian distribution. And what I meant by that is that, like, think about like any evaluations we get from, say, x1 through x3. The function evaluations f of x1 through f of x3 will have a multivariate Gaussian distribution with 3 variables. And more formally, basically, our Gaussian process is going to be defined by a kernel function and a mean function. And for any inputs x1 through xn, these evaluations, f of x1 through f of xn, will be distributed according to a multivariate Gaussian distribution, where the mean is the mean function evaluations on these variables. And the covariance matrix is it basically consists of the kernel evaluation on any pair of these input variables, x1 through xn. And one nice thing here is that we can also incorporate the noise model so that we can model the noise in the observation. For example, using an additive Gaussian noise. So to show an example of like typically how we use Gaussian processes, so basically we are trying to like model our function using a Gaussian process prior. So here is an illustration. We have like zero mean and all these. So the gray area shows the uncertainty, while the colored lines are the samples from the prior. And once we have some observations on the function that we're trying to model, what we can do is that we can condition on those observations and get the posterior for our Gaussian process, which luckily is also a Gaussian process by itself. So for the posterior Gaussian process, basically what you can see here is that by conditioning on these black dots, the observations here, we're essentially like pin down our uncertainty in those regions. And for regions where we don't really have many observations, we still have high uncertainty. And that also agrees with the samples we have from this particular distribution. So Gaussian processes are particularly nice in mathematically because we can write down its posterior mean and kernel again in closed form using conditional Gaussian distribution. And that actually plays a very important role in the process of Bayesian optimization as well. Okay. Any questions so far? Okay. All right, so earlier we have a lot of questions on what kind of acquisition functions we use. And here I'm going to give you an example for this. So this particular acquisition function shown here is called GPUCB. So it stands for Gaussian process upper confidence bound, and basically consists of the mean function and rescaled standard deviation. So the posterior mean and the posterior standard deviation. And what it's doing is that in every iteration, it's going to look at the input that achieves the highest upper confidence bound as the input to evaluate. And then we're going to evaluate its function value, put that new observation in the whole set of observations that we're conditioning upon, and then get the posterior again and continue. And the hope is that if we're balancing our mean and standard deviation in a good way, then we can eventually get to the global optimal. But in practice, the tricky thing is that, in fact, this particular parameter, beta here, is very hard to tune, and its value will determine a lot whether we can get very good performance from Bayesian optimization or not. Okay. So that's a brief overview of like what this problem is and what a standard approach is. But still, there are in fact quite a few difficulties in this field, including getting a good acquisition function, getting how to scale up this approach into a high dimension, how to do parallel evaluations in each iteration of the approach, and scale up to a larger scale of observations. And then the last the challenge is that, remember, when we are modeling our function, we're in fact using a Gaussian process prior. But how we can get that prior in an effective way is, in fact, also a very difficult task. So I've done some exploration in these different fronts, and in particular in this talk, I'm going to talk to you about some of our efforts in getting a better acquisition function, scaling up the input dimension, doing prior estimation with theoretical guarantee, and as well as some applications in robot learning. All right, so let's first look at how we can get a better acquisition function, hopefully without some additional hyperparameter by itself to tune. And the inspiration we have really comes from an approach that's called Entropy Search. And the very nice thing about it is that it doesn't really have hyperparameters, and it also comes from like an information theory motivation, and which makes this approach very appealing. So the basic idea here is that we're going to think about our acquisition function as some guidance for us to get to the global optimal, right? And in order to do that, we're going to look at the mutual information between the points we're going to query and the location of the global optimal, given some observed data. Yeah. Yeah. Well, so y is a random variable, and right, yeah. So it's like a Gaussian distribution. Sorry, what? So x is any input variable. So some input variable that we want to query. And so the no, it doesn't have like hyperparameters for itself to tune, like in the GPU-CP case. So yeah, but so I mean, basically the random variables here are the output y and the location of the global optimal. Because imagine like we have a distribution of functions, then its global optimal will also have a certain distribution. Yeah. So we can write this mutual information in two different ways for entropy, and we can like entropy search basically corresponds to the reduction in the entropy for the location of the global optimal given the point we're going to query. And the predictive entropy search corresponds to the case of the reduction in entropy for the point we're going to query given the location of the global optimal. So all these are nice, and there are actually also approximation we can do in order to estimate those expectations or the entropy for the global optimal. But the problem is, if our input x star or the global optimal x star is slightly high dimension, here I'm not talking about 50 or 100. I mean, it's something like 4 or 3 or 10 dimension. In that case, this will already make our acquisition function quite expensive to evaluate. So we're going to look at an alternative way of doing this. And the idea here is that instead of looking at the location of the global optimal, we're going to find the mutual information between point to query and the max value of our function. So essentially what we're doing is that we're moving from a high-dimensional variable in the input space to a one-dimensional variable in the output space. And again, for this particular mutual information, we can write it down in the form of reduction in the entropy. So in this case, we can show it in the reduction in entropy for the function value given the one-dimensional global max value. And the very nice thing here is that For the first term, in fact, this particular variable is has a Gaussian distribution. So its mutual information, is very easy to obtain. And for the second term, because we know that if we know the max value of the function, then all the other function values will be smaller than that. So that, can be effectively approximated by a truncated Gaussian distribution, for which case we also know the closed form entropy for that particular variable. And then in order to estimate this particular expectation, we can draw samples for the y star max values, and then write it down in a nice closed form. All right, we don't have to worry about what it is right now. So the only remaining question is, how can we draw samples for these max value y star? So we have a few different ideas, and here I'm going to show you one that's particularly effective. So remember that we know the function can be approximated by a Gaussian process distribution, Gaussian process, and then basically what that means is that for every input, f of x is a Gaussian, has a Gaussian distribution. So for any inputs, we have a Gaussian distribution, and then in fact, by the Fisher-Tippin and Denko theorem, what it says is that the maximum of a set of IID Gaussian variables is asymptotically described by a Gumbel distribution. So although our variables for f of x are not really IID, we can still sample some representative points in the input space, and then approximate the max value of those representative points by a Gumbel distribution. And then in that case, sampling from a Gumbel distribution for the max values will be very easy. All right, so let's try to put this together and see how this particular approach works. Basically, once we have some observations for the function, we do the posterior estimation. And given the posterior estimation, we can sample a set of those y stars. And then we can use those y stars to define our acquisition function. We can maximize our acquisition function in our iteration and get the xt, evaluate the function at this particular xt, and then put that particular evaluation back to the set of all the observations we have. So this is how this particular approach works. And but that's not the end of the story yet. So remember that we are, in fact, moving from a high-dimensional variable to a low-dimensional variable. In fact, one-dimensional variable. There's the question of, in this process of, switching up these concepts and trying a different variable for the mutual information, what do we lose here? And then the other question is, how can we better understand this particular acquisition function? Okay, so I'm going to first answer the what do we lose from experimental perspective. So remember that earlier we've seen the predictive entropy search approach, and in that case, that approach in fact samples the locations of the global optimal x stars. And then for our approach, we're sampling the one-dimensional global max values. So both of these approaches tries to sample these variables. And then we're in particular going to look at one notion of the regret, which is defined by the difference between the actual maximum value of the function and the best observation of the function value we've seen so far. So for PES, we look at the case where it samples 1 x star, 10 x star, and 100 x stars. And then what we can see is that as the number of samples for their x stars grow, the performance of PES is also getting better. And then we look at the approach that we have, the MES approach, and it samples different numbers of the y stars. And what we observe is that for the same number of samples, the MES is in fact performing better than the PES approach. And then for the MES approach themselves, it seems like having more samples for the white stars don't really give us a lot of benefits. So this is also, so another benefit we're getting is, in fact, the runtime. So for PES approach, as the number of samples its sampling grows larger, the runtime also grows larger, and in particularly, sort of like grows in a linear way. While for our MES approach, for different number of samples, the runtime for one iteration of the Bayesian optimization process sort of stayed the same. All right. So in fact, the benefits of using just one sample also showed up in our theoretical analysis for this particular problem. And basically, what we can show is that if we're just sampling one max values, we can already show a decrease in the regret. So we're basically bounding the regret by a value that decreases to 0 as the number of iterations goes up. And in fact, this is also the first regret bound ever shown for the entropy search approaches. All right, so we don't really lose much. And then now the second question is how we can understand this acquisition function. And in particular, like why having just one sample of Y star is already giving us very good performance. So we're now looking at the case where we just have one sample of this Y star. And what we can observe from this particular expression is that it's in fact just a function on the gamma Y star of X. So you can view the gamma Y star of X as like this Y star minus mu t minus 1 X divided by sigma t minus 1 X. And if we look at our acquisition function as a function of the gamma Y star, what we observe is that it's in fact a function that's monotonically decreasing for the input. So what this means is that maximizing our acquisition function is essentially equivalent to minimizing the gamma Y star of X. So, so interestingly, we can also show some connection of this kind of approach to the GPUCB approach that we've seen earlier. So what we can show is that if we set our beta parameter in the GPUCB approach to be the minimum of the gamma Y star of X, then the GPUCB approach will arrive at the same solution as the MES approach. So basically, what these analyses has shown us is that we can really view the MES approach with one sample of Y star as a way to smartly tune the hyperparameters for some existing approaches. So we've talked about the GPUCB approach, and then another approach is in fact called the probability of improvement, which I didn't talk about here. But basically, we can show like some connections among the existing approaches to the MES approach with just one sample of Y star. All right, so that basically concludes the first section, and we have some this work was mainly done about 2 years ago, and we have MATLAB code available, and then there were also some Python implementations by open sourced package called GPFlowOpt, done by some other groups. And so next, let's think about instead of just staying in 5-dimension, 10-dimension, how can we scale up these kind of approaches to much higher dimensions, like 50 or 100? So it's a very challenging task to scale up Bayesian optimization approaches to high dimensions, mainly for, so there are a couple of reasons, and the two main reasons that we sort of come into agreement upon is that, one, we are trying to optimize our acquisition function. So it's cheap to optimize, it's not really cheap to optimize. So it's cheap to evaluate. It probably has closed form, but we're basically evaluating our acquisition function in the same space as our original function. So our acquisition function could also have multi-peak, and finding the global optimal for that acquisition function can be very computationally challenging for the high-dimensional input space. And another problem is that we're using a Gaussian process to model our function, but estimating a nonlinear function in high-dimensional space will typically require a lot more data. And then, in fact, if we look at the typical regret bound that we get, it has a exponential dependency on the number of dimensions for the input. So statistically, it also has some challenges. And in order to overcome these two particular challenges, one approach that people use is to use an additive Gaussian process to model our function instead of using a Gaussian process itself. So by additive Gaussian processes, what I mean here is basically that we are going to view our function as a sum of function components. And for these function components, we're also going to assume that each function is only active on a subset of the input dimensions, and they don't overlap. And then for each of these functions, we're going to assume it can be modeled by a Gaussian process in a low-dimensional Gaussian process. All right. And then the sum of these Gaussian processes will also become a Gaussian process. So in this case, we can optimize our acquisition function in a block-wise way, and then we also get lower complexity of functions, so that we don't need that many data points in order to recover these function components. So that sort of like overcome both of these challenges that I mentioned before. But the question is, how can we get the additive structure? How do we know how this function can decompose to different function components? Or like, what are the input dimensions that different function component is active upon? So in this case, in order to think about like learning something, we really need to come up with some representation that represents the thing that we're going to learn. And in particular, in this case, we're going to view this representation as a decomposition indicator. And it's defined by a z vector. It has the same number of dimension as our input. And each element will denote the index of the function that that particular coordinate of input belongs to. So for example, if we have a function f0, f that is decomposed to f0 plus f1 plus f2, and this is its decomposition, then basically, because the first, second, fourth, and eighth dimension of input belongs to f0, then we can fill in 0 to these particular coordinates. And then because the last coordinate belongs to f2, then we're filling z to have 2 as the last coordinate. All right. So the question is like how we can learn this particular vector z. So the idea is we're going to do probabilistic modeling, and we're going to view this as sort of like an LDA type of process, but not really. So what is going on here as a generative process is that we're going to say that we have some hyperparameter alpha. We have a parameter theta that is distributed according to the Dirichlet distribution parameterized by alpha. And our z vector for each dimension, it's a sample from the categorical distribution parameterized by theta. So that will define our decomposition structure. And then given some parameters that governs the Gaussian process, we can generate a function f. Given that function f and input x, we can get an observation y. So once we define this process, the question is really how we can learn the posterior of z given all our observations. And we can do this very easily by doing Gibbs sampling. And it has very easy updates once we integrate out the theta variable. All right, so we compared our approach to different cases of setting these decompositions. One is using fully partitioned Gaussian process. Another is without any partition, so using the plain Bayesian optimization. Also, two approaches that we call it heuristics here, but they basically optimizes the data likelihood with respect to the decomposition structure, and also the true decomposition. And finally, our approach, which we call the structural kernel learning, SKL here. And so the interesting thing here is that our approach is, in fact, even performing better than the case we use the true decomposition. And our conjecture is that it is able to do that because when it's doing Gibbs sampling in the beginning, it doesn't really have the real the optimal decomposition that we can get. So it's able to do some more exploration in that case. So we also tested these approaches on a 14-dimension robot pushing task. And it's also, so we don't really know if it has any additive decomposition structure for that particular function. But our approach is still able to perform better. All right. So actually one interesting thing of these type of additive, sorry, yeah? Uh-huh.
You're partitioning and decomposing your input space.
Uh-huh.
Is there any intuition behind what would be in one? What would get partitioned together?
Yeah, so basically, yeah, that's a really great question. So I think you can understand it by thinking about the posterior inference phase. Basically, what we're doing is that we're trying to optimize the data likelihood. And if our decomposition aligns well with the true underlying decomposition, then it's going to get higher. Data likelihood. So that's how we're preferring the decomposition that aligns well with the underlying one. And then you can think of it as you can think of the Gibbs sampling process as doing some sort of local optimization for those variables. Yeah. Yes.
How do you define how many functions to decompose?
Yeah, great question. We set it to be the number of input dimensions because it has, that's the maximum that we can get to. All right. Okay. So let me tell you about one interesting thing we found for using this kind of additive decomposition structure. So we had we found some interesting connections of this particular approach to the evolutionary algorithm approach. So basically, I mean, evolutionary algorithms is a kind of population-based optimization heuristic that that has like very long history in AI, and it uses like mechanisms inspired by the biological evolution. And one of the mechanism that it uses is in fact called the crossover operator. And basically, what it does is that it's creating. Let me show you. It's creating the new points in the new population by randomly exchanging coordinates of the good points that we already have. So, so the interesting thing here is that we realized Bayesian optimization using additive GPs are sort of doing something similar. And let me show you what it's doing. So here we're showing an example of a two-dimensional function. It's really a tall example, but and then this is acquisition function. This is our estimated function, and in the acquisition function, once we have a good value, so in the yellow part, then it actually creates it propagates a bump along the coordinates of that good point. And as we are getting more observations, for example, these 3 observations there, and for those observed good points, for example, the -1, 0, and 2, 2, both of them are creating some bumps in the acquisition function, which resulted in the query points, which are exactly the crossover points of those good points. But the difference to the evolutionary algorithm approaches here is that we are actually learning the coordinate partitions instead of doing it in a purely random way. Okay. So this is basically, I mean, how we can get a better acquisition function and sort of like use the additive Gaussian processes to construct approaches that can scale up Bayesian optimization to much higher input dimensions. So I only have 15 minutes left, I realize. So there are 2 things that I would love to share with you, which is a more recent work we have on prior estimation and some of the robot learning work. So how about we'll just vote. How many of you want to hear about the prior estimation? Okay, cool. What about robot learning? It's sort of equivalent. Okay. All right, so, yeah, this is really hard. Okay. All right, so I'm going to devote like half of the time to each then. Okay, for prior estimation, so basically what we've seen so far is that we are using Gaussian processes to do as a prior to model our function f, but when we're using this approach in practice, we don't really know what this prior is, right? So there are a few things we can do here as a workaround. One is to, once we have some observations, we do maximum likelihood, or we do like hierarchical base to estimate what could be a good Gaussian process. But those kind of approaches actually create a problem which I view it as a chicken and egg dilemma in Bayesian optimization. So basically what this means is that what happens is when we're doing the model estimation, we're doing this from the data that's being collected, right? And then when we're collecting the data, we're actually assuming that our model is already very good. So this resulted in 2 problems. One is that theoretically we don't really know whether we have any regret bound when the prior is unknown. And at the same time, if we're using a bad setting of these prior distributions in Bayesian optimization, the approach will perform very poorly and will seem to be a bad approach. So the idea here we have is to really break the circular dependencies between the data and the model estimation process. And what we're going to do is that we're going to learn this prior from some past experience with similar functions instead of from the function we already have at hand. And the assumption here we have is that we can collect the data on the functions that are sampled from the same Gaussian process prior. So, so we call this meta Bayesian optimization, but it's really aligned with the multitask or transfer learning type of approaches. So here's roughly an illustration of how it works. So we've basically we're viewing this process as like two phases. One is the offline phase, and one is the online phase. And in the offline phase, we observe like all these functions. And we can estimate our Gaussian process prior from all these evaluations from these functions. Once we get the prior, in the online phase, our goal is to optimize a new function. We can use this prior and then construct unbiased estimators of the posterior, and then use a variant of the acquisition functions we've seen earlier. So they can keep doing this until finding a global optimal. So the interesting thing here is that our estimators for the posterior, in fact, also depend on the number of functions we've seen in the offline phase. And in particular, the more number of functions we've seen, the more certain we are about our prediction, which sort of makes sense. And the good thing about using this approach of like carefully tuning these estimations for the posterior and the prior is that we can get we can in fact obtain a regret bound for the case where we don't really know the prior distribution, which is really something that people haven't done before. The assumptions we're using here is that we have functions sampled from the same Gaussian process prior, and we have enough number of those functions. And then given some t new observations on our new function, we can show that with high probability, our regret is going to approach a small value, which is determined by the probability here and the observation noise. So in the case where we have small observation noise, then we also have small regret. Okay. So let me skip some details of how we did the estimation, and we can do like continuous parts, some results. All right. Basically, we're performing better. Okay. So, all right, about robot learning. So a lot of my work is really inspired by the question of how we can put the learning ability in the robot so that it can, so that it can do stuff in the world, right? So Bayesian optimization sort of captures the case of deciding for one action, but then if we really want our robot to be effective, we want it to be able to solve more complex and long horizon problems. So, for example, this is trying to make a cup of coffee with some ingredients on the table, and it will use like a bunch of different skills, like stirring, scooping, and here it's trying to cook and serve the green block. You can think of it as the broccoli, the lab version of broccoli, and it's really also using like a bunch of different skills like placing, picking, pushing the button, and so on. So one key question here is how we can compose these different skills together in a relatively in a good way so that eventually we can get our task done, right? And so the the kind of approach that we typically use is to build in a task motion planner. So you can think of a task motion planner as doing some sort of search in the space of our skills. And so by skills, I really mean like a piece of program where it takes in some parameters. It could be like discrete or continuous. And then according to that parameters, it tries to execute some policy until termination. And then when it's trying to do the search for these different skills, it needs to sample the continuous skill parameters and then do the search on both the discrete and continuous variables. All right, so I mean, this is really a one-page, really simplified, probably oversimplified view of this approach. But the thing to notice here is that if we just do pure forward search, it's going to be very unlikely to work because our solution, in fact, lies in a very constrained space. And in order to enable the efficient search, what we really need are models of the preconditions and effects of the skills so that we can operate with them in an effective way. So very quickly, I'm going to give you an overview of like what kind of precondition and effect models we're using here. So for example, if we're thinking about model the skill of pouring, so this really assumes that we already know how to pour, we know the policy, but now we want to describe what this is doing and in what situation the pouring operator can do the thing. So the desired effect is that, I mean, we can pour into the right cup with the liquid in the original cup, right? But in order to achieve that effect, there are certain preconditions we need to satisfy, including the fact that the cup contains the liquid, obviously. The robot is already holding the cup. The shapes of these cups, the relative poses of these cups, the control parameters for the pouring parameter, and eventually some constraint on all these parameters, which basically specifies the relation that they need to satisfy in order to arrive at a pouring skill that achieves the desired effect. Okay. All right. So how is this related to all the Bayesian optimization stuff we've seen so far, right? So I mean, it's really about like how we can actively learn these type of models. Because if you think about learning these models, these precondition and effect models, I mean, we're really trying to like capture all these conditions. So the question is like how we can do this without using too much data, since I mean, getting the data from robot is expensive, and then even if we use high fidelity simulation, it's still like we want to save some time, right? So some ideas, in fact, from Bayesian optimization could help in that case. And okay, so then the other thing is that once we have these models, we also need to consider how we are going to supply the parameters to the planner. So how we can do the sampling so that the planner can do its job in an effective way. So those are these two questions here: how to learn the condition, how to sample, and in fact, a remaining one that I won't really talk about is we also need to like figure out what variables in the environment are relevant to our skills, so as to like complete the loop of learning these models. And I'm going to show you quickly like how sampling the parameters actually can use like Bayesian optimization to achieve very good performance. So let's imagine like we are still in that search tree and we're doing pouring. And now we're going to sample the continuous parameter, let's call it x. And basically, you can view this process as trying to sample different x, and then we can get some observation from the planner that basically gives us a value of how this X contribute to finding a final plan, or whether there is a final plan or not. So we can keep doing this. Okay, wait. So we can keep doing this, and at one point we need to ask ourselves, oh, what is the next X that we want to try? So we can view this problem as, well, okay, some problem with the pointer. So we can view this problem as of like sampling these skill parameters as a black box function optimization problem. And then basically what we can do is that we can try to use Bayesian optimization to solve it. And the nice thing is that we can, in fact, also try to estimate our prior using the past experience of planning. So that search node does not only appear in one search tree. It can appear in many different planning problems. And we can extract those information out and use that information to estimate a better Gaussian process prior so that we can have much better planning performance in the end. All right, so that concludes my talk. So as a summary, I mean, I introduced what Bayesian optimization is and talked about a few challenges and our approaches. And I hope I also sort of conveyed what our robot learning work is in this domain. And I would like to thank all my collaborators and advisors. If you have any questions, feel free to ask.